Okay, are you able to see my screen? Somebody answer?
No, we can see your screens.
So we'll move to the next aspect in influential statistics. Pair t-test, that is comparison of means. So comparing between two classes, comparing between the performance of 10th standard A section, B section, how it was and all, or so some what you call some product is done today and what's the same product is done tomorrow. So how are you able to compare it? So at that point of time, we'll be using this parity test. So that is exclusively for comparison of. So we will see the difference, like why we have to use it and all. So I think I have to open that data set 7.1. I think I have shared this thing to everybody. So I've got 10 records. So before and after data. So what is the data? Okay, a product P121 is subject to a heat treatment process during its production. So it is required that the length of the product not be changed too much to heat treatment. Samples of the product are drawn before and after the heat treatment. Test if there is any significant change in length due to the process. So sample data before and after of the process are given below. Both the data before and after the process are approximately normally distributed. So already we assume that it is normally distributed. So this assumption has to be made by the analyst trying to do it. So that has to be kept in mind. Otherwise, what happens is like, of course, when I say that that question always arises in every mind, are very inquisitive people and all ask. No, normal is not the end of everything in life. At least for academic purposes, we take this thing, and that too, this is for a class where it's a bridge course or something like that. That is, so we cannot deviate from the fact that if I try to do examples from other distributions, that will be a challenge. So it will be, of course, try to do it for other problems or something like that, where especially engineering problems, scientific problems, or even life science problems. So at that point of time, there is an assumption that it is not always any column of data is always not normal. So we need to go to other distributions also. If you have other distribution, I can make it normal and try to apply this. So that's a force fit kind of a thing. So to make life easy for us who are analyzing it, we try to do it. But yes, people who are doing actual experimentation and all won't deviate and all. And for that thing, the formulas and all, if I assume it's a Poisson distribution, the way it has to be calculated and all is different. Interpretation also tends to be different. So that is also that. Please keep it in mind. So let me not confuse saying that no, is for this linear world everything is normally distributed. No, it not. That is 100%. Yes, definitely there are other distributions for that process and all. So things become complex and all. So at that point of time, yes, as the data comes, we have to analyze it, and for that other formulas are there. And today what happens is like relying on the tools. For example, Excel may not solve it for us. Maybe we have to go to a research software like R and solve it. Python also doesn't solve this problems of other distributions and all. Python is very good in a production environment. So for research purposes, R kind of softwares are used. Definitely R will solve the problem. Interested people can refer the documentations for other distributions or something. Or you can ping me. I can send you details of that thing for anybody who is interested. So keeping that thing in mind, let's try to do like I have two data set, one before treatment and one after treatment. So for this, what I have to do is what I have to proceed further. So for this thing, I frame the null hypothesis, the alternative hypothesis. So this has to be set by the analyst, the user or whatever it is. No software will do it for you. Only thing is that it may give you an indication of the yesterday's class, if you remember. So the variances were approximately 1. So it give a direction that whether I have to assume equal variances or unequal variances or something like that. At that point, it will help you like that. But it is us who will have to set it. So person, a human being is supreme here. Please do not depend on the software. Or if a process is set for anything like continuously, somebody in your process and all, you have joined a new process and all, somebody has set it, might be there is some experiential learning in that thing. So for that kind of a thing, yeah, we follow that process. Probably somebody has done it for 2 years. Might be a process is set. So we go to the fact that yes, whatever the hypothesis set by your predecessor or whatever it is you may call it. So that is true. Of course, after some time there might be changes and all, but that continuity is there. But it is you as a person has to. So please repeatedly I say that concentrate on the hypothesis testing. It's a very tricky subject, not very easy as it looks. How you frame it, why you frame it, what context, that has to be kept in. So since I have two things like, so before treatment sample mean is some mu1, after treatment sample some mu1. So my null hypothesis is mu1 is equal to mu2 and the alternative is mu1 is not equal to mu2. Easily we have set it. Usually this can even in a complex situation, the simple hypothesis is set because if we solve this only, then we can go to the, we have to read between the lines. Something things are not coming in our favor or something like that, or it is not working something correctly. So that point of time, we may need to change. So that's where our understanding about inequalities in mathematics comes to be. So I have this data now. So I have got select t-test, pair two samples for means here. So sample the t-test, pair t-test. So that is there. So yesterday we selected two sample assuming equal variances kind of a thing. So today it is pair two samples. So that is readily available in Excel. So you can get it. So let's try to do it. So following me in doing this thing, so I go to data, blocking, data analysis. Dialog box is small. At least my laptop is small, that's why it comes like this. I don't know, or I don't know how to make this bigger. By zoom also, the sheet will zoom, not the dialog box. Okay, two sample me for means and I say okay. So variable one range, say that is before, variable two range after. I have labels with 95% confidence. Only in medical research, we change this number to 0.01. Otherwise, it will be 0.05 by default. So let's stick to it. So that has become a standard, especially in what you call other, apart from medical research people, because in medical, out of 100 people, at least 99 will leave. Only one can die. So that's a thing. In business, you can sacrifice 5 people can die. So for 95 is the thing which you are trying to do it. So some kind of very raw way of understanding this. So we said that our confidence to say about 95% here. So that is what we call as alpha in the thing. So theoretically, so that is there. So I get an answer here. So I do have to check for the output range. Okay, I'll put it in here. Enough. So I say okay. So have so mean for the before, mean for the after, the variance, observations. So have something which are common to this. So I mean to say these results are common. So can I margins and no, I can't do it. Okay. So this for both of them. Wrap text should yeah. So this is for both of the things. So before and after. So this is the answers. Now we have to interpret like what each one of them means here, because that is where our expertise should be there. So software has done it for us. So this test is a two-tailed test. We are checking for the equality of looking at p-value for two-tailed test. The value is so 3.04. So it is after 11. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So then it should be 304. So definitely this is less than 0.05. Our alpha level. So in scientific notation it will come. So is the thing actually we are getting it or simply I'm typing it? Two tail. Am I right? Correct. So value. So which is close to 0. This is less than 0. So thus null hypothesis is rejected. That means that the current treatment has an effect on the increase of the length of the product P121. So mu1 is not equal to mu. So that also, that's a subtle difference in this thing. So what is my hypothesis here? So I assume that mu1 is equal to mu2. Definitely no. So the value, calculated value less than the 0.05. So the alternative has to be taken into consideration. Mu1 is not equal to mu. So and that is supported by the fact that so one is 2107.7, the other mean is 2185. So it's not a question of rounding and all cannot be done here. So subtly there's a difference between the mean from one before and one after. So that's why the alternative is accepted here. So there is an effect of increase in the length of the product after the treatment. That's the answer we try to give it. So let me pause here for a moment. Any doubts, anything you wish to say? Everyone. As compared to the last class, we had that student T test of the what we had here. Yeah, that's for the one sample or two sample to a sample. Any question? Anything you wish to know? Anything which you wish to tell me? So any challenges in testing hypothesis? Okay, I don't have any questions. Hopefully, I feel that you have understood it. It's the way which we try to do it. The two-tail test and a one-tail test. We come to a conclusion about this answer. So there are some other exercises also. So please try to do this thing. Only thing is like you have to enter this data. I think I have not given this thing. So they are different from this. The first one is mu1 is equal to mu. Second one is mu1 is less than mu2. So the question they have posed is, help Rajesh in assessing if the new drug has an effect on the health of patients infected with the bacteria. So that's I don't know what is that. Rajesh is the R&D development of department of some pharmaceuticals. Is testing the effect of a drug on the patient infected by a disease caused by a kind of bacteria. For this, he measures the health without administration of the drug and also after administration of the drug. So the health status is indicated by rating also, because there are many things which a doctor or a researcher try to find out. So it's a rating means like a combined index value. For example, BP, sugar, and many other parameters, heart rate, and also all say about 10 columns of data is mixed to one index or one rating or something like that. That is analyzed. So before, how the healthy individuals, after administration of the drug, how it looks. So health status is indicated by a rating. Assume that the data before and after the treatment are normally distributed. So that we say very much important. So statistic, that is why, so only at certain aspects this gets challenged. Like for example, that normally is why we have to say normally distributed, why it was not. See, before and all, when it was discovered and all, it might have been. Today, of course, many things have come. Only thing is like, even then also they provided, as I was talking about few minutes ago, like you can transform it to a normal distribution or for an assumption. That's also possible. So that has to be kept in mind. So this is also a very good example. Here, mu1 is less than mu2. So I don't know what the answer comes for this is like so see the author also has mentioned. So we have a less than symbol in the alternative hypothesis. So that's why very much about the inequality we studied. So here, so that is less than the value of 0.7. Null hypothesis rejected. We arrive at the conclusion that with the alternative hypothesis, that which implies that the new drug has a positive effect on the health of the patient. So there is a some kind of a change is there for that thing. So that is how we try to understand it. As I say, all the drug-related issues or something, quality issues, especially I don't know if you are engineers and you know about NIST standards or MIL STD standards. So anybody is a mechanical engineer here? Nobody? Okay. So people do know that what are those standards and so that standards, these are all very much, without that acceptance, people will not move forward at all. So for that thing, you need to apply this kind of test. So very, very valid. Even when we do large scale data and all, we may compare it and all. That time also, these results are very much, because this is the only proof you can show to anybody. Of course, you may not talk in the front of a client or something like you pair t-test with unequal variance, that and all will not be. We tell that So there is a subtle difference between after administration effect or something like that. So if I made a change to a process, yes, definitely the change has an effect on that particular thing. These are something which you can bring out. And if you do a project in your MBAs and all, so the hypothesis testing is one template also. If you see, that is very, very important. You have to bring the project in whatever area, whatever, it's not a matter. But this hypothesis testing is a must should thing as part of your research. So some more things, very good examples are there. So they have not set hypothesis and all. We need to set the hypothesis. So let us convince. We'll move to the next aspect of large samples, where I move from away from a t-test and I use what is known as a z-test. Why this t, z and all are given? Due to the, so I don't know, like t distribution known as a student's t. Student is a name actually, or it was a student of somebody or something like that. That's why that is named like that. That is also named something based on some understanding like that. So don't get confused and all. So let's move to the Z test comparison of means where I have large samples now. So let me close this. So I have got here about 30 or 31 observations. So I have something known as group 1 and group 2. What is that context? So here the situation is sample size is greater than 30 and the variance of the population or the sample is known, then in that case that test is. So I should know variance of the population here and it should be more than 30. So who will give this thing? So in a real life problem, who will provide this thing? So it is not that we get the framed questions and all to us. All we get is like what the problem we have to solve it, what's the data which is available at the client side. You have to take those things based on that thing, you have to frame an hypothesis and try to solve it. So where the sample size is 30 and the variance of the population or the sample. So at that point of time, I use that. So assess whether the two samples given in table 8.1 belong to the same population. Sample variances for group 1 and group 2 are 0.99 and 5.29 respectively. Assume the original population is normally distributed. So here also everything comes for normality. Normal is predominantly seen here. So my hypothesis is, what is the thing? So here population mean for group 1 is 1. Population mean for group 2 is 2. Mu1 equals to mu1 is not equal to it. What I try to take the hypothesis here. So I have got sample of 2 groups. So that test sample for means. So if the sample size goes beyond 30. So go to data analysis. So variable one range. So variance known, hypothesized mean difference, no, that's not the case. So variance known is there. So what is that has been entered here. Digital edition is really the trouble. I'm not really happy. Okay, 0.99 and 5.29. 0.5.29 labels out range. So these are commonalities for both of the things. So this is not at all considered. Okay, that is two tail values and a mean. So mean for the first group is 3.80, group 2 is 6.51. So how to prove it? As can be seen, p-value true tail is 1.74. So that is 1.74 is. So what that 4, 5, 6, 7, 8, 1, 7, 4. So definitely the less than 0.05. Null hypothesis is rejected, alternative hypothesis is accepted. Thus, the two samples do not belong to the same population. So, if I have to explain it, so one population, P1, P2. So, especially in this case, so I think the sample, small sample from this thing is sample from this. So there is no chance that it is not from the sample is not from this thing. It's so both samples differ. So choice of the samples we have taken is from two different populations, not from a single population. So that's what it is. Alternative method to arrive at a conclusion. So I have this normal distribution drawn here. So rejection region is the slightly shaded gray area, and so this is known as the totally 5% of area level of significance. So to the left of the screen is minus infinity, to the right of the graph is infinity, middle one is 0. So this is a normal curve. So normal distribution goes from minus infinity to plus infinity. The z value minus 6.0203 falls in the gray area on the left side of the screen. So this falls under this shaded area. Hence, null hypothesis H0 is rejected, H alpha is accepted. Thus, we arrive at the same conclusion as above. So, I have to put it in a very correct way. Here, 0, the minus side of things, the plus side. At minus 6 point or something like that comes under this area. So, we interpret that as Hence, null hypothesis H0 is rejected, H alpha is accepted. Thus, we arrive at the same conclusion. Both ways we can interpret it. So, thus the two samples do not belong to the conclusion. So, any questions here? What is the difference you perceive from the t-test testing? Yes, can somebody answer? What is the nature of the difference?
Zero, is it zero?
Yeah,
Will
the
plus
value
or minus?
is 0. So it falls to the left of that normal distribution. So that's why we conclude that. So that doesn't belong to the samples which you have. There are two samples there. The sample we assume that it belongs to the same some population, Indian population, but no, it's not India. So India plus Australia. So one sample came from India, other sample came from Australia. So that's how we try to interpret it. So definitely when we see that also, it's the same. We do this. So in a real life situation, say for example, if you are analyzing, say the company is same, if it has two different plants where some things are manufactured, we take a sample of in a week or something. So it is supplied to the analyst like to analyze and all. So it's told that it's from the same population. But when you try to analyze and go back to the your manager or to the management and say that no, it has come from two plants. What we have to say? Prove them wrong that this is not the case. You are given the wrong. It came from two plants, but you told that it's from the same population. In a real life situation, actually, a hypothesis is something like you have got two samples, so it is above 30. So, for example, you have got each 10,000 samples. So, column 1 has 10,000, column 2 has 10,000 samples. We try to compare it. We'll prove them saying that no, it does not come from the same plant, manufacturing plant. It has come from two different manufacturing plants. So, that's how we have to interpret. So, that was about this thing. There is quite good other things also which you can see. Looks good. We know this is an assistant manager of production department. He is concerned that two samples from two different lots might have been mixed. So he wants to know if two samples taken belong to the same lot. Assume the original lots to be normally distributed. So he takes the data about the weights of the toys from the records and they are shown in table. I don't know, this is some American movie. I think it's about some scientific or about medical research. I don't know. It's about yes, Harrison Ford's The Fugitive. Who has seen that movie? I think all are aware of Harrison Ford, right? The actor.
Yes, yes.
So, so his movie, especially if you see The Fugitive, especially in the last, he says that somebody gets the credit which for the research he has done. So he's put in jail and all, falsely implicated and all. So at that point of time, he's a medical researcher and a practicing doctor or something like that. So he has discovered something and somebody mixed up the samples and proved him wrong and he was put to jail. So I think the last climax scene and all has him going to a medical conference with the peer or is the fellow worker and all would have manipulated that thing. So that's the kind of an example. So how to prove it? It's not you can show that you have switched samples, but you have to do it. So a court of law also requires that kind of a. So you have to prove before the judge like this is the kind of thing will happen. So that's how you have to think and do it. It can be to any domain, any problem statement. That's how we have to. So he is concerned that two samples from two different lots might have been. So this happens actually, especially QC departments. So, and one more thing, probably you should have asked me why all these examples of production. Might be this professor has a background in industrial engineering or something. She might have worked in industry a lot, so that's why she gives a lot of examples. So that is also there. Why not from other things? Not all will have that kind of a people. It has been predominantly in certain domains, you can do a lot of things. Other domains are evolving, or you might not find many examples. Or you have to manufacture a example. So that's not good. You have some theories, some assumptions. Based on that thing, whatever the domain you have and the data which you get it, that you have to keep it in mind. Looks like an interesting example. Maybe to enter and do it. So what is the answer? So for this thing, variance of the two samples are not found or not given. So you need to use the where function first. Use that thing. So as you notice it, variance for the first sample is 1.07, other is 1.44. So certainly you are seeing a lot difference here. So even though this looks very simple and all, see the way you have to correlate things. Because you have to think in the whole picture and try to answer it. So there it was stated by the client or something like that. Here you need to calculate that thing, put it, and you get some result. So what is the analysis? So Vinod can conclude that the samples came from two different lots, or it has. There was one more movie, I don't know. It was also something, I don't remember. So two American research, one is a research PhD, the protagonist of the movie, something like that. So these are some kind of best examples, like to really make an understanding. Of course, it may not be really for the work which you are doing or something, but definitely you can build that understanding. That's important. So moving away from the large samples and all, now what we are studying is about analysis of variance. So have a t-test, a z-test. So why does it come? So till now we had a single sample, two samples, or a variant of two samples, equal variance, unequal variance. Variance was given, variance was not there. Extent of permutation. So apart from that thing, so if we have a situation something, let us take the example of car buying behavior of three groups, namely IT professionals from Chennai, Mumbai, and Bangalore. We would like to know if there is a real difference between the buying behaviors of the three groups, or is it attributable just to chance? Anova can be used some sort of marketing example with a cover of consumer behavior. People ask like how exactly measure consumer behavior. Where it bring this understanding. That's something there. So the car buying very much there. So about 8 years back, we have done something here in this kind of a thing. So Toyota had launched some of the vehicles about 6 to 8 years back, I think. So, I remember the sample survey was done in, of course, the 5 cities, the 4 things like Chennai, Mumbai, Delhi, Kolkata. Bengaluru was added because we were here. So we had to find out like what's the kind of consumer behavior which we need to find out of the car buying behavior. So we had used a stratified sampling in that case. Stratified sampling is like so I already have divided my concentration towards the metros or whatever we may call it. So that one sampling has so in that thing I need to do a simple random sampling. So we were told that there is in each city, especially the city jurisdiction had, of course, if it is beyond Bengaluru, we may not consider it. So it should be in the corporation limits of any city. So we had so many what you call uh, Toyota showrooms there. So each city we picked up about 2 or 3 showrooms. So that's a stratified approach we went about. Of course, we have a software also to decide like how to really choose. We give all those names and all for that software where it has to be picked up and all. So it will pick up which showroom. It's by random. That's all thing. There's no intervention by us. Right. System will pick it for us, but we have to supply names and all. So city also we can pick. We have all the cities and all, and what are the showrooms we need to pick up at that point of also. There are sampling software which pick up, but we have to provide the input correctly to that. It will not do anything for us. We have to put it randomly, it will pick it up. So then we devised an that's known as devising an experimental design. So we created the survey, it was there. So it's not like that we have a questionnaire, people will answer and all. No, it's very difficult that way. So it's like observing people who come and all, what are the questions. So what we do is known as a pilot study. So we may do in 1 or 2 cities, in 1 or 2 showrooms, come to a conclusion. So all those learnings are translated to a tab. So these tabs are given to the person, like for all the salesperson, the showrooms and all, there are a tab, for example. So here, based on the questions asked, and we had framed based on certain questions during our pilot. So that has been taken and translated to. So the person who comes for buying and all. So I am talking about the IT professional. So they will first ask that, so which profession? So slowly they come and answer. So which IT means, you will click on that IT this. So then on other questions and all. The IT professional also will be asking questions to the salesman. Salesman also will want, because we had asked him to get this thing and this was approved by Toyota itself, and we had to take the confidence of the distributors also, or car dealers or whatever you may call it. Everybody will know that we are doing it, but nothing will be known to the person who is coming and seeing the cars. It was for Toyota itself. That's how we do. So now we have many groups. So beyond 2 is what which we try to do. Car buying behavior of 3 groups. That's one kind of an example to really conceptualize the problem. So our example has a trainer predicts that students will learn most effectively in the early mornings as opposed to afternoons and nights. He randomly divides 24 students into 3 groups of 8. All students study the same subjects during morning, afternoon, and night. After studying, all students take a 10 marks multiple choice test. Assume the original populations to be normally distributed and their scores are given in the table. I also have that thing here. Oh no, close this. Yes. Scores of students. For students who have taken it. So three different things. So 8 into 3 is 24 data points. So it might be 3 cities, 3 points of time, whatever it is. However, your problem context is there. Take that into consideration. So we frame the hypothesis. Population mean for group 1, mu1, 2 is mu2, 3 is mu3. So our null hypothesis, mu1 equals mu2 is equal to 3. Alpha is the alternative is, sorry, at least one of the means among mu1 and mu2 is different. I mean to say, consumer buying pattern from between Delhi and Mumbai may differ with regard to Bangalore. Bangalore is something a different crowd itself. Even though you have IT professionals, Delhi and Mumbai, but Bangalore, as it's known as an IT capital for India, so the buying pattern usually changes of the IT professionals in Bangalore. So who observes this and all? Like a thing like people have done a lot of studies on this thing. They have a set pattern of this buying behavior. So how to frame the hypothesis is mu1 equals mu2 is equal to mu3. At least one of the means alternative hypothesis I frame. Oh, I select it. So the Anova single factor. So input range I have to give. It's by columns, label in first rows, out. Let us try to do this. I go to data analysis, go up here, Anova single factor, put range. So it is grouped by columns. So it is 3 columns, morning, afternoon, and night. Labels in the first row, output range. Let me put it here. And I say OK. So whatever you see here, this kind of a thing. Why we bring this is that as the data size increases and all, the modeling challenges changes and all, and this is the kind of outputs you will try to find in your linear regression. The first step is the modeling exercises. So that's what we try to bring. That's also a statistical way, but we have all this. As I told you, whatever I have taught it, all the combination thing will come there. So here also you find between groups and all Anova. So what's the difference? So let's check. So this for 3 groups which we have found, morning, afternoon, night. The summary is this thing. What is the sum? What is the average for each one of them? As you notice, morning average is something different as compared to this. So if I try to round off this thing, so it might come up to 5. This might come up to 6. Let's try to do this. If I try to do home, okay, it's 4 and 6. It's not rounding up. Okay, no problem. And so this is it. I think morning actually differs from this thing is what I feel. I don't know. Let us try to do some magic and in our understanding. Okay, so I got the results now. At least one of them differs with what I have made the statement. Looking at the p-value, when this is rounded off to 3 decimals, yields 0.0. Definitely, that is less than 0.05. So we reject null hypothesis and accept alternative hypothesis. We conclude that the difference between the groups is significant at the 5% level of significance. Thus, there is a significant difference between the groups studying at different times. But so at least one means like usually people in the mornings who study really score well. Understanding which we try to bring it. So people doing studies in psychology and all try to do this kind of experiments or in the field of education itself. So people who study MEd and all this Master of Education and all, they do this kind of studies. So they will try to find out. That's why I told you the study is at least one mean differs. Definitely that mean differs. So that is shown here. So purposefully, if I put it this thing, so if I okay, 4 and 6 are somewhat near or something like that, but this falls under the one group or something like that. 8 is something out of the box. That's how we try to interpret it. So there is a difference, so I accept my alternative hypothesis. So let me pause here. Any questions you people have, I'm happy to answer. So one thing which started with single, two, this thing, then we have come to three. All variations try to do it. Then answer your problem. Is anybody any question? The problem statement, context, and all matters. That I have to keep it in mind. As an exercise, you can try this out. So Rahul is in researcher. I don't know. He's in, I don't know, which field. I'm not sure. On a project on the careers of youngsters in various fields, he is interested in finding whether the incomes earned by youngsters after finishing are almost same. For this, he considers youngsters in three important fields, namely engineers, auditors, and lawyers, and compares their income. It is assumed that the results of the analysis of the samples can be used to generalize the results for the school. Assume that the original populations are normally distributed. So here also, mu1, mu2, mu3, at least one of the means differ. So what is that thing? As you notice here, average of the average this thing, incomes of engineers are 32,700 or something like 33,000. And incomes of auditors and lawyers are 31,000. So there is a difference. So at least one of them really subtly differs from the other. There are very good examples here. So you can try it out. Any questions here before I move to the next task? Okay, I don't have any questions. So let me move to the next aspect. I think we had already done this thing. I had shown you. We had to create a contingency table. So or pivot table, but more meaningful from a statistical well, this one. So we need to analyze it. Yeah, pivot table, fine, that is done. But how to analyze it? How to bring something like we studied test, let test, Anova and all. There's some kind of a test we have to yes. What we have to see is known as a chi-square test. So that's what we try to do now. So let us consider, suppose there are two modes of conveyance, cycling and walking, and we would like to know whether male cycles more or female cycles more, and whether males walk more or females walk more in a group of males and females. That is to say, if there is any association between conveyance and gender. So this is achieved by using chi-square test. So what does it do? Chi-square test is used for three purposes. To check the goodness of fit of a distribution with the theoretical, to check homogeneity of a variable across different populations. For example, category of food preference among male and female groups. Third is to check independence or association between two variables, that is cross tabulation. That's what we do. We did what is known as the cross tabulation, and output is contingency table. So cross tabulation in Excel is basically a pivoting, what we did. So I have sales of three types of cars in three regions. So test if there is any association between regions and types of cars. So we framed the null hypothesis H0 and H alpha, sorry, HA. There is no association between regions and brand of cars purchased. There is significant association between regions and brand of cars purchased. So this is English. There is no association. There is association. That which we try to find out. So these are the observed values. The expected values are calculated in figure 10.2. Expected value for a cell is calculated by multiplying the corresponding row total and the column total dividing by the grand total. So I get some values like 29.52 and all, etc. etc. So that is done here. So observed values are given. I need to calculate expected values. So if you are using any software like R or Python or something like that, that will calculate for you all these things and give it. The facility is not there, but this can calculate an chi-square test. Expected value for the cell region is calculated as 90 multiplied by 82 divided by 250. Okay, try to do. So this is 28. Sorry, 90 multiplied by 2 divided by So here what I should fix, column E. So column E is fixed there. So this is the dollar sign or relative references and all. So D thing, so this portion has to be fixed. So I need to have taken this what E5. So that is hash 5 control. Am I getting correctly? $29, $19, $32. Okay. So if I have to take the sum of the standard back, correct? Sum of so either way, if I sum this thing, that is so this is observed. Expect so so this is the answer which I get with the ranges. So it is something like after decimal 18 zeros, it is definitely less than 0.05. Hence, the null hypothesis is rejected and the alternative hypothesis, that is, there is significant association between regions and brands of the car. That's the which we come to say about this. So, as a whole, between region and brand, gender and what you call income, studying that kind of problems and all, we try to come up with. Have an observed value which we get from pivot. We create a expected values as I told you. Then we do a chi-square test. Framing the hypothesis is done. I got certain examples right out. Case study also. Ram is the manager of a logistic company. Drivers in the logistics company seem to be taking traveling times quite greater than the ones usually required to travel. He wanted to determine the reasons why this was happening. As a first step towards it, he decided to study the time taken from point A to point B for trips between A and B. So he wanted to find out if a driver was assigned a job, he preferred some routes more often. It's schedule of the frequency of the preferred routes of the drivers between A and B during a month is given there. So driver 1, driver 2, driver 3. So what route he prefers. So these are observed. Vis-a-vis what are the alternatives. So there is no association between driver and the routes. There is significant association between drivers and the routes. Here also it is less than 0.05. Certainly there is a difference. So it is conclusion is fine. Then there is one question posed here. Ram can now investigate further and arrive at the reason where the drivers were losing time while traveling and why they are doing so. So that becomes this is an objective study or an objective answer. Subjectively, you have to delve deeper and find. So I think today I had all these things. So we'll my next class on Monday study this non-parametric. People have any questions? Feel free to so that I'll be happy to answer. Anybody, any question? So we have about 2 from the non-parametric statistics and one thing to knowing about correlation and the linear regression. We give a beginning to multiple linear regression or the predictive modeling. Probably we'll have 2 more classes because some theory I have to give with using when I teach about the linear regression. Okay, so if people don't have any questions, please stop the recording.